Assalamu alaikum viewers, please like, share and subscribe this channel. Links of PDF files used in this video are given in description. So today's lecture is about ozone hole, and in this lecture we will see how the layer of ozone is depleting day by day due to air pollution. So first of all we will see what is ozone layer and where it exists and what is its main function. Actually, we are living in the biosphere. The biosphere means the sphere which contains life. So, the biosphere is composed of all the ecosystems on Earth where there is life. And this biosphere is divided into three types of further spheres, which are called as the atmosphere, the hydrosphere, and the lithosphere. In atmosphere, the air surrounding us is the part of atmosphere. The water bodies that are contained on earth makes the hydrosphere, where the solid dry surface makes the lithosphere. Now let's see what is atmosphere. The atmosphere is made up of layers of gases that surround the earth. These layers provide living things with air to breathe. These also trap heat and regulate the temperature of the earth, and they also create protective layer so that the harmful radiations that are coming from the sun cannot destroy the living organisms or materials that are contained on the earth. So it means the atmosphere is further divided into various layers, and each of these layer has its own function. So as we have discussed earlier, the atmosphere is divided into several layers. These layers are called as troposphere, stratosphere, mesosphere, thermosphere and exosphere. The layer in which we are living and most of the weather phenomena are occurring in this troposphere, whereas the second layer is stratosphere, and the main constituent of stratosphere is the ozone, and it is found in this layer, and it protects the harmful radiations that are coming from the sun. Next is the mesosphere. This is the coldest layer which protects us from meteors, because in this cold temperature the meteors will burn up and they will never reach in the troposphere. Next is the thermosphere. This is the hottest layer because it absorbs the sun's radiation, and auroras mm, are the phenomena of color that are happening in this thermosphere. And the final layer is called as exolayer, and this exosphere then stretches into the space. Most of the satellite bodies are found in the exosphere. So these are the layers of the atmosphere. So the most important point is that ozone is actually lying in this stratosphere. There are two types of ozone. One is called as surface level ozone or ground level ozone, and it is formed during smoke. Whereas the other main layer of ozone is called as stratospheric ozone, and this is also known as ozone layer, and its main role is to protect the earth atmosphere from the harmful radiations that are coming from the sun. So ozone is a molecule which is made up of three oxygen atoms and is mostly found in the stratosphere, and it represents only a tiny fraction of atmosphere. However, this stratospheric ozone layer is very important for life on earth. uh, the troposphere actually is lying from earth's surface to 15 kilometer above, and then from 15 to 50 kilometer is the width of whole stratosphere layer. So without ozone, the sun's intensive UV radiation would sterilize the earth's surface. With the weakening of this shield, more intense radiations like UVA, UVB and UVC will have a longer exposures at the surface, and they will lead to quicker skin cancer, and will damage to the environment, and will also reduce the crop yield. The surface ozone or ground level ozone that is formed during the formation of a smoke is a harmful or dangerous product, and this is also called as bad ozone. And when sunlight initiates chemical reactions in the air involving pollutants, particularly a family of gases called nitrogen oxides along with volatile organic compounds, produce the ground level ozone. So the main content of stratosphere is this ozone layer. Now we will see why these UV radiations that are coming from sun are divided into UVA, UVB and UVC. So we have drawn here electromagnetic spectrum that contains radiations that are coming from the sun. So if we see here, this is the ultraviolet region, this is visible region and this is infrared region. As we are moving from left to right, the energy of the radiations is decreasing. So if we see here, the UVA region is from wavelength 315 to 400 nanometer, whereas UVB radiations are from 280 nanometer to 315 nanometer, whereas UVC radiations are from 100 nanometer to 280 nanometer. So it means the most energetic radiations or ultraviolet radiations are UVC, then less energetic are UVB, and the least energetic UV radiations are UVA radiations. So if we see here in this diagram that UVA radiations that are coming from the sun are not absorbed by the ozone layer. So these radiations are slightly stored by the ozone or absorbed by the ozone, whereas most of these reaching towards the troposphere or earth surface. Then as we are seeing here that slightly energetic as compared to UVA radiation are UVB radiations, and they are almost more than half percentage of UVB radiations are absorbed by the ozone layer, and very tiny fraction is then reaching towards the earth, whereas UVC radiations, these are most energetic radiations and these are completely absorbed by the ozone layer and nothing is reached in the troposphere or earth surface. So in this way the ozone layer is filtering the harmful UV radiations, and most energetic or dangerous UV radiations are completely stopped, whereas UVB radiations are partially stopped, whereas UVA radiations are fractionally stopped by the or absorbed by the ozone layer. There are natural processes that create and destroy ozone in the stratosphere. These processes regulate a balance of ozone and form the ozone layer. So first of all, the ozone is created primarily by sunlight. When high energy ultraviolet C radiations strike on the oxygen molecule, then they split the oxygen molecule into two atomic single oxygen atoms. So in this way, these oxygen atoms then further react with oxygen molecule to form the ozone. So a freed oxygen atom combined with another oxygen molecule to form the ozone. Because there is so much oxygen in our atmosphere, this oxygen ozone cycle is continuously absorbing high energy ultraviolet radiations and completely blocking it from reaching the earth's surface. This process also creates some extra heat in the reaction, and that is why the upper part of the stratosphere is slightly warm in nature. The ozone formed here is very reactive and attacks other oxygen molecules in the air, so it can also generate oxygen in return. Also, this is why ozone is important to us, as ozone in the stratosphere absorbs UVB radiations and is converted into oxygen molecule and further into oxygen atom. So while ozone is continuously being replenished, it is also continuously being destroyed. Sometimes an ozone molecules react with oxygen atom creating two oxygen molecules, thus ending the cycle. So if the rate of ozone creation is equal to the rate of ozone destruction, then the total amount will remain the same. This is likely this is just like a leaky bucket. If you pour water into the bucket at the same rate that is leaking out, the level of water in the bucket will remain the same. Scientists have found that ozone levels change periodically with regular natural cycles such as the changing season, winds, and long time scale sun variations. Ozone also responds to the solar flares. Similarly, volcanic eruptions may inject materials into the stratosphere that can lead to the increased destruction of ozone. So, in overall, we can say that there is a balance between ozone formation and ozone destruction. Actually, in 1970s, the scientists suspected that reactions involving man-made chlorine-containing compounds could upset the balance, leading to the lower level of ozone in the stratosphere. Think again of the leaky bucket. Putting additional ozone-destroying compounds into the atmosphere is likely to increase the size of the hole in the bucket. So the larger hole causes ozone to leak out at a faster rate than ozone is being created. Consequently, the level of ozone protecting us from the ultraviolet radiation decreases. The ozone destroyed by man-made emissions is comparable or more than the amount of that is destroyed by the natural processes. Human production of chlorine containing chemicals such as chlorofluorocarbons, and these are mostly used as repellents in perfumes and sprays and spray paints. So these add as an additional factor that destroy the ozone. Chlorofluorocarbons are molecules made up of chlorine, fluorine, and carbon. Because these are extremely stable molecules, these do not react with other chemicals in the lower atmosphere, but exposure to ultraviolet radiation in the stratosphere breaks them apart and release the chlorine. So if we see here, this is the chlorine which has come from chlorofluorocarbon, and it reacts with ozone to form chlorine oxide and oxygen molecule. This chlorine oxide then further reacts with oxygen to form chlorine and oxygen molecule. Now this chlorine is again available to destroy the ozone. So free chlorine atoms that react with ozone molecules, taking one oxygen to form chlorine monoxide and leaving the oxygen molecule. So if each chlorine atom released can destroy only one ozone molecule, then the chlorofluorocarbons would pose a very little threat. However, when a chlorine monoxide molecule encounters a free atom of oxygen, the oxygen atom breaks up the chlorine monoxide, stealing the oxygen atom and releasing the chlorine, as we have discussed in the second reaction. So this chlorine which is released destroy another ozone molecules. So these two reactions happen over and over again, so that a single atom of chlorine acting as a catalyst and can destroy about 1 lakh molecules of ozone. So that is why the chlorofluorocarbons are very dangerous, even if they are in very less amount in the atmosphere. One good thing about chlorine is its too much reactivity. Actually, this chlorine does not remain forever in the atmosphere or stratosphere. Actually, it reacts with other molecules, such as it can react with methane, and as a result of which each produce HCl or hydrochloric acid, which is washed up or washed away via rain or acid rain. So therefore, if humans stop putting chlorofluorocarbons in the atmosphere, then the stratospheric ozone will eventually return to its earlier higher value. So next the question is that how the ozone is measured. Scientists have been measuring ozone around 1920s using ground-based instruments that look skyward. So data from these instruments, although useful in learning ozone, but it only tells us the ozone concentration just above the instrument. To get a global view of ozone concentration and its distribution, scientists use data from the satellites. So it means there are two ways of measuring ozone. One is via ground-based instruments and other is via space-based instruments. The way of measuring ozone is very simple. So we know from the measurements how much incoming UVB sunlight arrives at the top of Earth's surface about every second. So we also know that how much light including UVB is scattered by the air molecules in the atmosphere, that is called as relief scattering, and as it is shown in this diagram, and this is the same phenomenon that makes the sky appear blue. So we can calculate the amount of UVB sunlight that would make it to the Earth's surface if there were no ozone to absorb it. However, when we measure the amount of UVB sunlight from the ground-based instrument, then it is found that it is very much less than we calculated. So the difference is the amount of UVB absorbed by the ozone, and from that we can calculate the amount of ozone. Measuring ozone from the space based satellites is also similar, but you have to know the amount of solar UVB light that is back scattered and is reaching towards the instrument or the space based satellite. So, this backscattering or bouncing of molecules in the atmosphere is also called as relief scattering again, and this will be measured in the direction of satellite. This measurement technique is depicted in this figure. So, we can calculate how much UVB light the space-based instrument would observe if there were no ozone. However, the amount of UV measured is much less because the UV is passed through the atmosphere a second time. Again, from the amount of UVB that is missing, we can calculate the amount of ozone. So in this slide we will see what is the ozone hole is. The ozone hole is not really a hole but a thinning of ozone layer over the southern polar region. Every year since from 1978 there is a sudden rapid decrease in the stratospheric ozone level at the end of Antarctic winter. So here we are seeing that around October, the season of the year here creates a thinning of ozone layer. So during the long winter months of darkness over the Antarctic, atmospheric temperatures drops creating unique conditions for chemical reactions that are not found anywhere else in the atmosphere. The wind in the stratosphere over the polar region especially intensifies and forms a polar vortex which circulates around the pole. The transition from inside to outside the polar vortex creates a wind barrier that isolates the air inside the vortex and also result in a very cold temperature in at this region. At temperatures below minus 78 centigrade, thin clouds made up of mixture of ice, nitric acid and sulfuric acid form in the stratosphere. Chemical reactions on the surface of these ice crystals convert the chlorine containing compounds like HCl, which is harmless to ozone, into more reactive forms. When the sun rises over the Antarctic in the spring, like around September, light rapidly releases free chlorine atoms in the stratosphere. A new ozone destroying cycle begins. The chlorine atoms react with ozone, creating ClO. The ClO or chlorine oxide molecules combine with each other, forming a compound called a dimer. Sunlight releases chlorine atoms from the dimer and the cycle begins again. The polar vortex actually keeps the things inside and the ozone depleting air inside from mixing with the undepleted air outside the vortex. So the things remain concentrated here, and as a result of which in this region the ozone layer gets depleted. The ozone destruction continues within the polar vortex until the ozone level approaches zero at the altitudes where the reactions on the thin clouds have released chlorine atoms. Once the ozone has reached such a low level, so here we are seeing that the greater the blue color, the less molecules of ozone are there. So once ozone has reached such a low level, the chlorine atoms react with methane, filling the vortex with HCl. The low ozone persists until the vortex weakens and breaks apart. Then the ozone levels in the polar stratosphere begin to return to the pre-September condition, like in this stage. And due to increase in solar UV and the mixing of polar and non-polar air, the ozone levels are again regenerated, just like shown here. This slide actually summarizes the timeline of stratospheric ozone depletion and various observations. So the data is from the year 1965 to 2015, and there are various colors of bars, and we have two axes. On this side we have area of ozone hole. So these bars actually explain the area of ozone hole. Like if there is greater size of the bar, then it means at that time period there was a greater ozone hole, and if the area of the bar is small, then it means a small hole of ozone was present. And what are the different colors of these bars? So here we have a nimbus 7 toms, ep toms, and then here as eos, aura, and then meteor toms. So what are these? These are actually different satellite based measurements or programs of NASA that have used different types of instruments in order to measure the ozone level in the atmosphere. So the latest is this purple shade instrument that is representing NPPOMPS instrument. Whereas on this side of axis there is the quantity or emission of ozone depleting substances in the atmosphere, and these are in the quantity of megatons in year. So here we are seeing that the slope of the emission of these ozone depleting substances has increased. Now it is decreasing. The solid spherical represents actual observations of the data from the industry, whereas the uh, empty spheres explain the future projections, and this is not the actual data. So these are the things which have to be explained in this timeline of the stratospheric ozone depletion. So one more thing mentioned in this graph is that this line represents the emission of natural substances that depletes the ozone. So from 1965 to 2050, the concentration of natural ozone depleting substances has not increased and it remains constant. However, there is a massive increase of ozone depleting substances, like it is maximum around 1985 to 1995, and now it is continuously decreasing, and in the year 2015 and onwards we are predicting further decrease of ozone depleting substances. 1975, the United States Congress recognized the importance of understanding such atmospheric phenomena and directed the NASA to research and monitor the upper atmosphere in order to better understand the chemical and physical integrity of Earth's upper atmosphere. Daily space based observations of global stratospheric ozone levels, particularly over Antarctica, started in 1978. So, here we are seeing that the observations have been started, and first instrument that was used was called as total ozone mapper or toms. So these are the readings of the first instrument, which is called as nimbus 7 toms or total ozone mapper. The toms instruments on board multiple platforms provided observations of the ozone hole for about nearly 29 years, with the exception of 1995 data. After the TOMS instrument, then the Meteor 3 stopped sending data in the December of 1994. So Meteor 3 TOMS is actually the platform on which this TOMS Nimbus 7 was placed. The historical record of ozone depleting substances provided by the NASA instruments show the slowing of the depletion after emissions of ozone depleting substances were reduced. The Vienna Convention was held in 1985 and called out that ozone depleting substances are threat. Faced with the strong possibility that ozone depleting substances are the threat, gases containing halogens such as chlorofluorocarbons could cause serious ozone depletion. So policymakers from around the world signed the Montreal Protocol in like 1987, and at 1987 the concentration of ozone depleting substances was at highest. However, after the Montreal Protocol in 1987, limiting the chlorofluorocarbon production and usage, we are seeing that there has been a tremendous decrease in the ozone depleting substances. As a result of Montreal Protocol and its subsequent amendments and adjustments, the ODS emissions decreased substantially between the 1990 and in the year of 2015 and now. So some other things are also mentioned in the timeline. So first global surface observation of chlorofluorocarbon was recorded in like 19 before 1975. Similarly, the chlorofluorocarbons were hypothesized as ozone depleting substance by Rowland and Molina. And then in 1975, the Congress reported and directed the NASA to have look into the matter of atmospheric concentrations of ozone. The Antarctic ozone was first discovered like in 1985 by British Antarctic Survey, and at this point in 1994 the lowest value of or the deepest ozone hole was recorded, and it was only 73 Dobson units thin. Similarly, then in 1995, Nobel Prize in Chemistry was awarded to Paul Crutzen, Maria G. Molina, and Frank Sherwood Rowland for the discovery of the ozone hole and the cause of ozone depleting substances. At this level, we are seeing that a small hole caused by major stratospheric warming was produced. So, the small means that the ozone hole was not created in a greater proportion because of the mixing of the air. So it means when the conditions are colder, then there is greater production of ozone hole. And at 2005 or 6, the greatest ozone hole depletion was noted, and the record mean size of the ozone hole was 26.2 square kilometer. So this was recorded for a period of about 1 month. So this was all about the dissection of this diagram. So the title of this slide is A World Avoided. What if the countries of the world had not agreed to phase out production of ozone depleting substances? Were scientists right about predictions of catastrophic ozone loss which led to the signing of Montreal Protocol? To answer these questions, atmospheric scientists at NASA and other research centers decided to create a model using computers to simulate the atmosphere with and without restrictions in ozone depleting substances. Like the world would be like this with the Montreal Protocol, in which we will ban the ozone depleting substances, and we are seeing that the ozone molecules concentration will be like this. However, the world would be like this blue in color without Montreal Protocol, and without Montreal Protocol means there will be no ban on ozone depleting substances. So the ozone molecules will be in the concentration of 100 or less than 100 Dobson units in just 2064 year. However, these are the projections in the real world. As in the real world now, the Montreal Protocol has been activated. So it means now after 1992 there was a complete ban on ozone depleting substances. However, their abundance is only now beginning to decline because the chemicals stay in the atmosphere for like 50 to 100 years. The peak abundance of chlorofluorocarbons in the atmosphere occurred like around 2000 and has decreased by roughly 4% to date. Stratospheric ozone was depleted by 5 to 6% at the middle latitudes. So if we are seeing that in those periods of time the ozone hole was created very deep, and it was depleted like by 5 to 6% at middle latitudes, but has rebounded a little in recent years. So now we are at this stage, and at this stage the ozone hole is getting to recover again. The largest recorded Antarctic ozone hole was recorded in 2006, with slightly smaller holes since then. The real world simulations predicts the recovery of ozone layer to above 300 Dobson units around 2050 to 2060. So this all is because we have activated the Montreal Protocol, and the production of ozone depleting substances such as chlorofluorocarbons is in complete ban nowadays. So this slide describes the timeline of the size of ozone hole created with the passage of time. So we are seeing that in 1979 there was no ozone hole, and after then the ozone hole was created in the southern pole of Antarctic region, and it was then increases day by day, and this all was that due to the production of ozone depleting substances. And here in this year of 1995 there was no data. After then we are seeing that the ozone hole was almost constant in size except in 2002, and in 2002 there was a global warming air, as a result of which the vortex mixing of cold and warm air happened, and the ozone hole at this time was not created too much greater in size. After then it then again created in size. However, nowadays if we see here that up till 2011 it was too much greater, but now in 2012 it has reduced, and now the ozone hole is in at this stage. This is what happens, that we have complete ban of ozone depleting substances. And if we have the ban on ozone depleting substances, then why this ozone hole has been created like in 2010, 11, 12? The reason is that the ozone depleting substances remain 40 to 50 and some things about 100 years in the atmosphere. So after 100-year cycle, when they will be consumed, so then there will be again recovery of the ozone hole, and the ozone layer will get again thick. So this was data from 1979 to 2012. So this was all about today's lecture. I hope you have well understood this lecture, but still if you have confusion, then let me know in the comment section. I will respond to your queries as soon as possible. Okay, thank you. Allah Hafiz.